Welcome back to Physics 142. We've been talking about the idea of electric potential, which is essentially very similar to the idea of potential energy, just potential energy from a point charge, except that we realized that it's helpful to sort of normalize by the amount of charge, and that removes sort of a lot of sign issues that we have between positive charges and negative charges. Positive charges and negative charges can both agree on values for electric potential. So last time we wrote down that if you know what the potential energy is, due to some charge configuration or some amount of charges, we can calculate this electric potential by just taking the potential energy and dividing by Q. Similarly, if we know what the potential is, if we multiply by Q, we can figure out what the potential energy is. We also realized last time that there's a connection between electric field and electric potential. And specifically, the connection between electric field and electric potential is that if you imagine wandering through some electric field, if you take some path and walk through an electric field, so we take a bunch of little steps dl through some electric field, if we add up all of those steps, then we get the change in potential. Now, importantly, when I wrote this equation down, I forgot to add the minus sign, so I have it in a different color here. All right, we realized there's actually a minus sign in this equation. It's actually the opposite of that integral. But the idea is still that if you take an electric field and you integrate it over some path, that gives you a change in the potential energy. So what I'd like to talk about today is what if we know that we have, say, a point charge, and we don't necessarily know the electric field, but we know the amount of charge Q, and we know the distance r that we are away from the point charge. And what I'd like to show you is that the value for the electric potential at the place where that charge is calculated. We can calculate it by just doing kq divided by r. All right, so how much potential is there at a place where there's a point charge? It's kq over r, and I want to show you where that comes from. So to get an idea where that comes from, I want to think about some positive charge. All right, let's take a positive charge here, positive q, and let's think about moving along some path. We'll pick a spot to start here. We'll pick a spot, we'll call that spot A. And we'll maybe want to go to a different spot, call that spot B. That's the spot where we want to end. And we're going to take and wander and take some path from A to B. All right. Now A is going to be some distance away from that positive point charge. We'll call that distance r sub A. And B is going to be some distance away. We'll call that distance r sub B. And what we want to figure out is, well, how does the potential change going from A to B, right? Just generic, any spot A, any spot B, right? How does the potential change? Well, to do that, the one formula that we have so far where we're calculating change in potential is to take the potential at B minus the potential at A, whatever the value is at B, compare that to the value at A, and we know that's going to be the opposite of the integral from A to B of E dotted with dl. Now, to make any progress in this, to actually calculate this in terms of R and Q, the values that we were given in the problem, we need to deal with this dot product. So dealing with dot products just means taking the magnitude of E times the magnitude of dl times the cosine of the angle between them. And now we need to write these things in terms of the variables that we know. And, well, maybe this is a little tricky, but, well, first of all, do we know what the electric field is for a point charge, for a spot some distance away from a point charge? So let's think about some spot on this path, right? And so we'll take a spot here, and we'll take a spot that's a distance r away from that point charge. And we know that there's an electric field then that points radially away from that point charge, right? That's what the electric field does from point charges. And we know what the magnitude of the electric field is. The magnitude of electric field for point charges some distance away is just going to be k times q divided by r squared, right? That's the magnitude of electric field from some positive point charge. So that's good. We can replace the E with something with Q's and R's in it. But what about this dl cosine theta? Well, let's think about that a little bit. So what is dl? dl is my little step along this path, right? That's dl, is my step along the path. And theta is the angle between E and dl, right? So, but how do I write that in terms of r, in terms of the distance that I am away from that positive point charge? Well, let's zoom in on this a little bit, all right? Let's think about some step dl. So here is my step dl. And let's think about the electric field vector. So maybe here's my electric field vector. And there's an angle between them. That's angle theta, right? And so, well, if we think about how much r changes during this little step dl, right, let's think about how much r changes in the little step dl. Well, r, that radial direction is along E, right? E is in that radial direction. So a change in r, a little change in r, dr, is going to be point along that electric field direction, right? That would be my little change in r is dr. And what you might notice is that dr is just a component of a right triangle with dl, right? And specifically, it's the cosine theta component, right? It's the component that's touching the angle. So what we can write is that dr is just dl cosine theta. Or if we look back at our equation, dl cosine theta, well, we can replace that with dr. And so now we can rewrite our integral as an integral over radius, over the distance we are away from Q. So we can start at RA, some distance away, and we can end RB, some other distance away. So let's write that down. So it's minus the integral from now RA to RB, right, of KQ over R squared dr. There we go. So now we have to evaluate this integral. That's not too bad because, well, let's see, k and q are both constant. So we have minus kq times the integral from RA to RB. K of just now we have 1 over R squared dr. And the integral of 1 over R squared, that's an integral that, you can, you've probably done in your calculus class before. Integral of 1 over R squared is just minus 1 over R, right? So we can now write this, and I'll move the board up so we get a little more space to write out what this integral is. So this, there we go, let's move over here. So this is just going to be minus KQ times minus 1 over R. And now we got to evaluate that at RA and RB. So the minus signs cancel. And this is just going to turn into plus KQ over RB. And then minus positive KQ over RA. And that is VB minus VA. So we realize that the amount that the potential changed is just KQ over RB. KQ over RB, that's the potential at spot B. And KQ over RA, that's just the potential at spot A. So how this is normally written is now we can think about, well, imagine let's take spot A and move that sort of, as far away as we could, right? The further we move A away from this charge, right? The larger we make the radius, the smaller and smaller the potential value gets, right? Or we could also think the closer we bring, say, B to the charge, the larger the potential gets. So if we want to know what the potential value is at positive Q compared to sort of a value, well, where would the potential sort of want to drop off to zero? Well, if we go infinitely far away from the charge, it's going to drop off to zero, right? And so sort of as a matter of definition, what we usually say is that V equals 0 at R equals infinity. So if we take A to be at infinity and B to be at the position of our positive charge, or at some position, I guess it doesn't have to be at the positive charge, right? But to be at some position, what we get is that the potential at any spot around this charge is just going to be V at any place, right? Any place is just going to be KQ over R. And so that's the formula that we started with up here, is that for a point charge, V equals KQ over R. Now, what if you have many point charges or a continuous charge distribution? Hang tight, we'll get to that in another video.